Good day, AP Stats. I'm going to cover in this video the first part of lesson 11.1, which deals with chi-squared distributions. Those of you who've taken AP Biology, this will be some review for you. So we're going to take a look at M&Ms and the distribution of colors in M&Ms. And this is according to the M&M makers, Mars Incorporated. 13% of the candies are brown and red, 14% orange, 16% green, 20% orange. I think I said orange twice, and 24% blue. So if you were in class, I'd give you candy and you'd like that, I assume, but alas, this is not going to happen in class. So chi-squared distributions deal with a categorical variable. We're looking at the color of the M&M, but the difference is we're looking at the entire distribution, not one specific proportion or two proportions. So you're going to see some slight differences in the four-step process here. So it says, do the data provide convincing evidence? That tells me this is a test. So I'm going to follow my four-step process: state, plan, do, and conclude. There are going to be no parameters. There's going to be no symbol because we're talking about an entire distribution. There's not a symbol for that. So what you're going to see here is just the null and alternative hypothesis solely in words. So the null hypothesis is that the Mars claim of the color distribution of M&Ms is true. And the alternative would be the Mars claim of the color distribution of M&Ms is not true. So basically, the null hypothesis is going to be the claim of the distribution is true, and the alternative is going to be that it's not true. We're going to test at a significance level of 5%. That's our default. They haven't told us anything otherwise. Occasionally, they'll say 1% or 10%. I don't think we've seen that in class yet. Plan. For our sampling distribution, CVS, we're going to check still the random condition. Ideally, I would have handed out to you M&Ms in class. They would have been a random sample. So I'm just using some class data from our prior year. It was a simple random sample of 78 M&Ms. For variability, we're sampling without replacement, so we have to check the 10% condition. 78 is less than 10% of all M&Ms. And shape. This is going to be a little bit different. We have the large counts condition for categorical data. This is going to be the large counts condition, but what we're actually going to check is different. There's something called the expected counts, how many of each color we expect to get. And I'm going to come back to this in a moment, but all expected, and you're going to have to list expected counts are greater than or equal to 5. And you'll see that we haven't done that yet. That's going to be in the do step. Let me try to straighten this out for camera. Okay, so as we always do, we're going to name the procedure, conditions met, do a chi-squared. This is called a goodness of fit test. Goodness of fit. How well does the data fit the claimed distribution? Test with degrees of freedom. The degrees of freedom are the number of categories minus 1. So we have 1, 2, 3, 4, 5, 6 different colors. So 6 different categories minus 1, 5 degrees of freedom. Okay, for the do step. So I'm going to make a table here of what we have. So we have the color, we have the observed, and we have the expected. So color, we have brown, red, yellow, green, orange, and blue are 6 colors. We observed, this is what actually happened in the data. There was 10 brown, 10 red, 20 yellow, 20 green, 10 orange, and 8 blue. Okay, what we would expect to have happen is based on the claim. So we'd expect 13% of the candies to be brown, which is 10.14. Same thing for red, it's 13%, 10.14. Yellow and green, we expect them to 14% for yellow, 16% was the claim for green. Orange was 20% of 78, and blue 24% of 78. So I actually didn't do those calculations ahead of time. Give me a moment, and I'm going to run through those. 14. So for yellow, we expect almost 11. For green, about 12.5. For orange, almost 16, and for blue, almost 19. So obviously we can't get part of an M&M. The expected counts do not have to be integers. The observed ones have to be integers. So I'm not going to round these. They are what they are. Our test statistic is calculated a little differently, and our sampling distribution is going to look a little different, and I'll talk more about this in a minute. The test statistic, we take the observed count minus the expected count squared divided by the expected. All right, so we're squaring these so that we end up with a positive values. We're dividing by what we expect. The bigger the difference is, the more significant our data is going to be, because there's not much of a difference here, so that wouldn't be convincing evidence that the distribution is not true. So the bigger the difference is, the bigger our test statistic is going to end up being. So plus, if I do the next one for red, 10 minus 10.14 squared divided by 10.14 plus ... And then if I just do the last one for the blue, 8 minus the 18.72 squared divided by the 18.72 equals. So that's the work that I'm going to show for my test statistic. I'm going to show you on the calculator how to do this. All right. I'm going to need to enter the data into lists. So I'm going to go to my lists. If need be, I'm going to clear these out by just highlighting the list, hitting clear, enter. So in the list one, I'm going to put the observed counts 10, 10, 20, 20, 10, 8. And in list two, I'm going to put those expected counts. I'm not rounding these. They are what they are. Okay. Then I'm going to go to my stat test menu. Again, stat, hit the left arrow. And I'm just going to arrow up to chi-squared GOF test. I'm going to hit enter. And it's going to tell me, do you have the observed count somewhere? Yes, in list one. Expected, list two. Degrees of freedom are for us 5, 6 categories of colors minus 1. And I'm going to hit calculate. This is going to give me my test statistic, so 20.23. This gives me my p-value, and I'm going to come back to this contribution is what that stands for in a moment. So our test statistic is 20.23, and our p-value is 0.001 approximately. All right, the sampling distribution, I didn't draw it yet. All chi-squared distributions are skewed to the right. As the degrees of freedom increase, they become less skewed. But the sampling distribution would really look like this. It only takes on positive values. I'd have 20.23. I'm running out of room on the bottom of the paper, shading above. There's no such thing as a two-tailed test for chi-squared. It's always going to be shading to the right, an upper tail. Okay. If I didn't use the calculator to get the p-value, what I can do is go to second vars, go to chi-squared CDF. This will look just like TCDF. If I put in that lower value, my test statistic, upper value, some really large number with 5 degrees of freedom, that's how I could get my p-value by hand if need be. Okay, that's it for the do step. On to the conclude step. We're talking what we always do, conclude, because the p-value equals 0.001 is less than alpha equals 0.05, so very unlikely to happen by chance. we reject the null hypothesis, which means there is convincing evidence that, and then I'm just going to talk about the alternative like we've always done. Mars claim of the color distribution of M&Ms is not true. Is not true. Now, anytime we reject the null, or if our data is statistically significant, this is only for chi-squared, we're going to do what's called a follow-up analysis. And basically, we're looking at what's the reason that this test statistic was so big? What specific color was it that caused that biggest discrepancy? So that's where I'm going to go back to the calculator with the contribution. And if I hit the right arrow, basically what this is showing me, out of this sum of 20.23, what the contribution is for brown, red, yellow. So brown, the observed and expected were very close together. So if I actually calculated this out by hand, I'm going to get that 0.001. So that's a really small. Red, same thing. Yellow, 7.5. Green, 4.5. Orange, 2. And blue, 6.1. So yellow had the biggest. This one was about 7.5. If I did 20 minus that 10.92 squared divided by 10.92. So the way I'm going to do this last part, and this is going to be new, this is called a follow-up analysis. And we only do this if we reject the null. Basically, we want to know, why did we reject the null? Like, tell us some more information. So this is how I'm going to say this. The largest component or the largest contribution, I'm sorry, not component, the largest contribution to chi-squared was 7.5. I don't remember the decimal after that, because there were more yellow M&Ms than expected. Okay, so really the main reason we rejected the null hypothesis here is because we had so many more yellow M&Ms than expected. Obviously the blue and the green contributed, but not as much. All right, so that's just a video going through the 4-step process for a chi-squared goodness of fit test, talking about the follow-up analysis. In the next video, I'll kind of go through some of the details about the chi-squared distribution in depth.